Hello everyone, welcome to this presentation, and thank you for having me today. Now we will explore a very interesting paper titled Joint Offloading Decision, User Association, and Resource Allocation in Hierarchical Aerial Computing, Collaboration of UAVs and HAP, or shortly we can just call it JOR. The paper is by Amadou Nabi and Sangbang Mo, published in IEEE Transactions on Mobile Computing in 2025. Speaking of myself, I'm Mahdir Mim, a master's student in the Department of Computer Science and Engineering in Big Data at Chungang University. I'm working under the supervision of Professor Will Che in the Intelligent Networking Lab. My main research interests are fluid antenna systems and non-terrestrial networks. This paper is particularly relevant to my research because it studies cooperation between UAVs and a high-altitude platform, which are important components of future non-terrestrial communication and computing systems. Here is the outline of this paper. Let us begin with the introduction. Now let us look at this architecture more carefully. The system can be viewed as three collaborative computing layers. At the bottom layer, we have the ground users. This can be IoT sensors, cameras, smart vehicles, rescue devices, or mobile phones. Their primary role is to generate tasks. For example, a surveillance camera may need real-time object detection. A medical sensor may need to analyze patient information. A vehicle may need image processing for navigation. The problem is that these devices are usually resource constrained. They have limited battery, limited power processing, and limited storage. The second layer consists of UAVs. Because UAVs are physically closer to users, they can provide low latency computing support. We can think of them as flying edge servers. However, UAVs themselves are also limited. They have limited battery capacity and limited onboard processors. This leads to the third layer, HAP. The HAP is located much higher, but it can provide significantly larger computational resources and longer operational duration. So the entire philosophy of this paper is cooperation. Instead of forcing all tasks to stay locally or sending everything directly to the HAP, the system intelligently decides how all three layers should collaborate. Now, this slide explains how much computation actually flows through these layers. First, at the ground user layer, every device must answer a simple question. Should I compute locally or should I offload my task to a UAV? This is called a binary offloading decision because there are only two choices. Let us consider an example. Suppose a rescue camera captures an image. If the image is small and not urgent, the camera may process it locally. However, if the image requires complex AI inference, local processing may be too slow. In that case, the task is offloaded to a UAV. Another question appears. Can the UAV process everything by itself? Sometimes yes, but sometimes the task is too large. For example, video analytics or large image reconstruction may exceed the UAV's capabilities. Therefore, the UAV can split the task. One part is processed locally by the UAV, while another part is forwarded to the HAP. This is called partial offloading. Both finally, UAVs and HAP needed to allocate CPU resources. In simple terms, if many tasks arrive simultaneously, which task should receive more computational power? Urgent tasks may receive more resources, while less critical tasks may wait. Therefore, the challenge is not only where the task goes, but also how much computing power should be assigned to each task. Before discussing the proposed solution, let us briefly review existing research. Many previous studies considered UAV-assisted aerial computing. Some work studied only UAV-based edge computing. Others considered collaborating between UAVs and HAPs. Several works focused on user association, some focused mainly on resource allocation, others considered offloading decisions. However, most existing approaches optimize only one or two components. Very few studies jointly optimize all major decisions simultaneously. For example, some methods allow UAVs to make all decisions centrally. Others ignore partial offloading or user association. This creates inefficiencies because all these decisions are actually interconnected. This paper attempts to fill that gap by jointly considering ground users offloading, user association, UAV to HAP partial offloading, resource allocation. This joint optimization is the major novelty of SHORE. Now, what exactly are these objectives? The system aims to achieve three goals simultaneously. First, minimize latency. Second, minimize energy consumption. Third, balance the load among UAVs. These objectives are important because reducing only delay may increase energy consumption. Similarly, reducing only energy may overload certain UAVs. Therefore, it's a trade-off. This proposed Jory scheme attempts to find a good balance among all three objectives. To do this, the auto-reverse model communication and computation costs mathematically. Then they formulate an optimization problem and design an algorithm to solve it. Now we move to the system model. The system contains multiple ground users and 4 UAVs. Time is divided into equal time slots. At each time slot, every user generates one task. The task is represented as IMT equals to SMT, CMT, LMT. The equation is very important. The first term represents task size. This tells us how much data must be transmitted. The second term represents task complexity. In other words, how computationally difficult the task is. The third term represents latency requirement. This indicates how quickly the task must be completed. For example, two tasks may have exactly the same size. However, the one task may require simple data processing, while another requires AI inference. The second task would be much higher complexity. Similarly, emergency tasks may have stricter latency requirements. After defining the task, the next question becomes how much time and energy are required to process it. This leads us to the communication and computation models. This slide models the communication process. First, communication occurs between ground users and UAVs. The transmission delay is simply data size divided by transmission rate. This makes intuitive sense. Larger tasks require longer transmission time. Higher transmission rates reduce delay. The parameter AUMT is extremely important. It determines whether the task is offloaded. If equals 1, the task is sent to UAV. If it is equals to 0, computation remains local. Next, we have communication between UAVs and the HAP. Here another variable appears, IUMHT. This indicates what fraction of the task is forwarded to the HAP. If this value is 0, everything stays at the UAV. If it is 1, the entire task is forwarded. Values between 0 and 1 represent partial offloading. Therefore, these two variables determine the entire task flow inside the hierarchical system. Now let us examine the computation. For local computation, delay depends on three things: task size, task complexity, and device CPU capability. A more powerful processor naturally reduces computation time. The energy model follows the dynamic power relationship. This means increasing CPU frequency significantly increases energy consumption. Therefore, simply allocating maximum CPU resources is not always optimal. For UAV consumption, the UAV only processes the portion that is not sent to the HAP. Another important concept introduced here is UAV load. Load indicates how busy a UAV is. Imagine one UAV serving almost all users while another remains mostly idle. This creates bottlenecks and rapid battery depletion. Therefore, balancing load among UAVs becomes one of the major objectives. The HAP processes tasks forwarded by UAVs because the HAP processes significantly larger computational resources. It can handle complex tasks efficiently. However, reaching the HAP introduces additional transmission delay. Therefore, offloading everything to the HAP is not always optimal. The paper therefore computes the total end-to-end delay and total energy consumption. This includes local computation, GU to UAV communication, UAV computation, UAV to HAP communication, and HAP computation. This combines costs from the basis of the optimization problem. Now, the paper combines the delay and energy consumption of all ground users. First, dt represents the total delay required to process all tasks generated during time slot t. It is calculated by adding the delay of every ground user. Similarly, et presents the total energy consumed during the time slot. This includes energy used for local computation, wireless transmission, UAV computation, and HAP computation. However, delay is measured in seconds, while energy is measured in joules. Because they have different units and ranges, directly adding them would not be meaningful. Therefore, the authors normalize both values. Here, Dmax t is the maximum delay value at time slot t, and Emax t is maximum energy value at the same time slot. After normalization, both delay and energy are placed on a comparable scale. This allows the system to combine them fairly in one optimization objective. Now, this is the final optimization problem. The objective is to maximize normalized delay, normalized energy, and UAV load. The decision variables are four main things. First, A, offloading the decision from ground users to UAV. Second, I, part of task offloaded from UAV to HAP. Third, FU, UAV computation resource allocation. Fourth, FH, HAP computation resource allocation. The constraints ensure that one user connects to at most one UAV. Latency requirements are satisfied, CPU capacities are not exceeded, and UAV-HAP energy remains sufficient. Now we need an appropriate method to solve this optimization problem. The difficulty is that the decision variables are not all of the same type. The ground user's decision to compute locally or offload to a UAV is binary. Similarly, selecting which UAV serves a user is a discrete association problem. In contrast, UAV to HAP offloading ratio can take any value between 0 and 1, and UAV-HAP CPU allocations are also continuous values. A single conventional algorithm may not efficiently handle both of the decisions. Therefore, the paper divides the problem into two stages. The discrete decisions are solving using a traditional matching game-based algorithm. The continuous decisions are solved using an enhanced soft actor critic reinforcement learning algorithm. Together, these two stages form the proposed George scheme. This slide explains how ground users and UAVs rank each other. First, each UAV calculates a preference score for every ground user. This score considers the normalized communication rate between the user and the UAV, together with the UAV's remaining energy. A communication rate means that the task can be transmitted quickly. Considering remaining energy prevents a UAV with a low battery level from accepting too many additional users. Each ground user also calculates a preference score for every UAV. The score considers the channel rate, task size, task complexity, and latency tolerance. For example, a user with a large and highly complex task may need a UAV with a stronger connection and sufficient available resources. As a result, each UAV creates a ranked list of ground users, and each ground user creates a ranked list of UAVs. The association is therefore based on mutual preference rather than simply selecting the nearest UAV. This helps improve transmission quality while also considering workload and energy conditions. Now here are two algorithms used for ground user offloading and association. Algorithm 1 first calculates the preference scores. For every ground user and every UAV, the corresponding score is calculated using the equations from the previous slide. These scores are often sorted to create the preference list. Algorithm 2 performs the actual offloading decision and matching process. First, every ground user checks whether its task can be completed locally within the required deadline. If local computation can satisfy the latency requirement, the offloading variable is set to 0, and the task remains on device. Otherwise, the user is added to the unmasked users list, must find a suitable UAV. The algorithm then calculates the approximate number of users that each UAV should support. This helps distribute users more evenly. Each unmatched user proposes to its preferred UAV. If that UAV has available capacity, the user is accepted. If the UAV is already full, it compares the new user with its currently least preferred matched user. It may replace that user if the new match is more suitable. The process continues until all possible users are associated. After the ground user offloading and association decisions are completed, the remaining variables are continuous. The UAV must decide that fraction of each task should be sent to the HAP. It must also decide how much CPU resource should be allocated at the UAV, while the HAP must decide its own resource allocation. For these decisions, the paper uses an enhanced soft actor critic algorithm, or ESAC. In conventional reinforcement learning, the objective is to maximize the expected cumulative reward. Soft actor critic adds an entropy term to this objective. Entropy represents uncertainty in action selection. In practical terms, it encourages the agent to explore different actions instead of always selecting the same familiar action. The temperature parameters alpha controls the strength of this exploration. The reward is defined as the negative weighted cost of delay, energy, and UV load. Therefore, an action producing lower delay, lower energy, and better load balancing receives a better reward. This figure shows the overall architecture of the proposed drawer scheme. On the left side, the preference score calculation and GeoUA algorithm first determines which users offload and which UAV serves each other. These results, together with the current UAV and task information, are passed to the reinforcement learning environment. The actor network observes the current system state and selects an action. This action contains the UAV-to-HAP offloading ratios and CPU resource allocations of UAVs and the HAP. The environment executes this action and returns a reward and the next state. The system uses two critical networks instead of one. Both critics estimate the quality of the selected action, and the minimum of their estimates is used. This helps reduce overly optimistic value estimation. Past experiences are stored in the replay buffer, and the proposed method also uses prioritized experience replay. Shown as per in the figure, instead of treating every experience equally, it gives greater priority to experiences with larger learning errors. This allows the agent to focus on more informative samples and improves learning efficiency. This slide summarizes the detailed ESAC training process. At the beginning, the actor network, two critic networks, two target critic networks, and replay buffer are initialized. At each training step, the agent observes the current system state and selects an action according to its current policy. After the action is applied, the agent receives a reward and observes the next state. The complete transition consisting of the current state, action, reward, and next state is stored in the replay buffer. A priority value is also assigned to this experience. Samples with larger temporal difference errors are more likely to be selected during training. The critic networks are then updated so that they can estimate action quality more accurately. The actor network is updated so to select actions that produce higher rewards while maintaining sufficient exploration. The temperature parameter is adjusted automatically, and the target critique networks are updated gradually for stable learning. After repeated episodes, the algorithm obtains the optimized partial offloading and resource allocation decisions. Now we move to the simulation setup. The ground user's transmission power is 0.5 watts, while the UAV transmission power is 10 watts. Task size varies from 1 to 8 megabits, so the simulation includes both relatively small and large tasks. Task complexity varies between 600 and 750 cycles per bit, and the latency requirement ranges from 1 to 7 seconds. The ground users have relatively limited computing capacity, between 0.5 and 0.75 gigahertz. Each UAV has a computation capacity of 10 gigahertz, while the HAP has much stronger capacity of 50 gigahertz. For reinforcement learning, the model is trained for 1500 episodes. The mini batch size is 256, and the discount factor is 0.99. The parameter values are selected consistently with previous hierarchical aerial computing studies. Now let us examine the main simulation results. This slide contains several graphs, so I will focus on the major observations. The first graph compares the convergence of ESAC with SAC, PPO, and DDPG. ESAC converges more quickly and reaches a higher average reward, and becomes relatively stable and approximately 400 to 500 episodes. This indicates that prioritized replay and the enhanced relearning structure improve training efficiency. The other graphs examine performance as the number of ground users increased from 30 to 100. As expected, successful task completion decreases because the available computation resources must be shared among more users. However, Azure consistently achieves the highest completion ratio. It provides approximately 98% successful completion with 30 users and still maintains around 85% with 100 users. Task execution delay increases with the number of users, but Azure remains the best. With 100 users, its average delay is approximately 4.8 seconds. Azure also maintains an average UAV load of approximately 0.68 and energy consumption of about 133 joules per time slot at 100 users. Therefore, Azure does not improve only one metric, it simultaneously provides better task completion, lower delay, lower load, and lower energy consumption. This slide examines the effect of UAV computation capacity while keeping the number of ground users fixed at 80. As UAV computation capacity increases, the successful task completion ratio improves for all methods. For Azure, it increases from approximately 0.68 at the lowest capacity to around 0.89 at 10 GHz. The average task execution delay also decreases. For Azure, it falls from approximately 5.7 seconds to around 3.5 seconds. The average UAV load decreases from approximately 0.78 to about 0.47. Although the UAVs complete more work, the load ratio becomes lower because their total available capacity has increased. Energy consumption increases only slightly. Higher CPU frequency requires more power, but the tasks are also completed more quickly. Across every computation capacity setting, Azure continues to outperform the baseline methods. This shows that the proposed approach remains effective under different hardware capabilities and is not limited to one specific UAV configuration. To conclude, this paper studies a hierarchical aerial computing system containing ground users, UAVs, and a high-altitude platform. Its main contribution is the Azure scheme, which jointly addresses ground users offloading, user association, UAV-HAP partial offloading, and computation resource allocation. The author divided the original mixed optimization problem into two sequential stages. The GOU algorithm handles binary offloading decisions and user association through mutual preference matching. The enhanced soft actor critical algorithm handles continuous partial offloading and CPU allocation decisions. The framework also dynamically controls how many ground users each UAV supports during every time slot. Finally, prioritized experience replay improves the learning efficiency of the actor critic method. The simulation results also show that this combined design improves successful task completion while reducing latency, energy consumption, and UAV load. Finally, the authors identify several directions for future research. First, UAV mobility can be included. In the current framework, UAV locations are fixed, but mobile UAVs could reposition themselves according to users' demand and channel conditions. Second, the system can be extended from a single HAP to multiple HAPs. This would introduce additional association and coordination decisions. Third, cooperative computing among UAVs can be studied. A heavily loaded UAV could transfer part of its workload to a nearby UAV instead of always forwarding it to the HAP. Finally, satellites can be integrated with UAVs and HAPs to form a larger space air-ground computing network. These extensions could improve coverage, flexibility, and system resilience, although they would also create more complex optimization problems. That concludes this presentation. Thank you for listening and have a nice day.